Hi, my name is Preet Singh. I'm professor at the School of Material Science and Engineering at Georgia Tech. I'm going to introduce you to corrosion in this module. The main things which you're going to learn are understanding of electrochemical nature of corrosion. I'll introduce you to Faraday's laws and also introduce you to different forms of corrosion. Now, when we talk about corrosion, generally rust or uniform corrosion comes to mind, but there are many forms of corrosion and we'll learn about them as well. So if we think about metal corroding, metal corrosion is an electrochemical process, which means that it has two components, oxidation and reduction. In oxidation, metal undergoes oxidation, which means that it goes to higher oxidation state and releases electrons in the process. For example, zinc will go to zinc plus 2 ions and release 2 electrons. Similarly, iron can go to iron plus 2 or iron plus 3. Now, once these electrons are released, they have to be consumed. So that happens on cathode surface, and that process is called reduction or consumption of electrons. So in this process, oxidizer will consume those electrons and get reduced. And typical example is that dissolved oxygen in water may consume 4 electrons, giving 4 hydroxyl ions, or protons, which are available in any aqueous medium or acid. They may actually consume electrons and giving hydrogen gas in the process. The overall reaction or overall corrosion reaction can be written as metal in presence of oxidizer. In this case, it happens to be protons or acid. It will undergo oxidation, producing metal ions and hydrogen. So like any reaction, reaction will proceed if delta G or Gibbs free energy of this reaction is negative. But beauty of electrochemical reactions is that just by measuring the potential, or E, you can actually relate that to Gibbs free energy and determine whether reaction will proceed or not. Now, as I mentioned, it's an electrochemical process, but you don't need anode and cathode to be separate like shown here, which is typically the case in batteries where we have anodic side and cathodic side or cathode electrode. So in this process, you need an ionic current path. So anode and cathode areas, they should be connected through electrolyte or ionic current path, but they should also be electrically connected. If any of those 4 conditions, that means anode, cathode, ionic current path, and electronic path, they are missing, then the electrochemical cell or corrosion will not occur. So in the process, at anode, you produce electrons which are transferred to cathode. But the oxidation reaction rate is equal to reduction reaction rate, which means that if you want to stop or slow down oxidation, you can slow down reduction as well. Now for corrosion, when metal is dipped, these 2 anode and cathode or anodic and cathodic processes can happen at the same metal surface as shown here, that you can have oxidation of metal producing metal ions. At the same time, adjacent to that, protons can be consuming those electrons left behind, producing hydrogen gas. If we look at different forms of corrosion, you can think of corrosion as either uniform corrosion or localized corrosion. In uniform corrosion, for example, corrosion of ship or automobiles or bridges, infrastructure, or machinery, that is a typical example of uniform corrosion where you see rust throughout the surface and metal loss is similar throughout that surface. In localized corrosion, which has different forms like galvanic corrosion, de-alloying, or selective leaching, erosion corrosion, crevice, pitting, intergranular, these actually occur without any role of stress, and they occur in a localized fashion only in areas where passivity or inhomogeneity can lead to localized corrosion. Now, if stresses are involved, in that case you can have a phenomena which is called environment sensitive fracture or premature failure of material under applied or residual stresses. If it is monotonic stress, you can get stress corrosion cracking. If you have corrosion cyclic stresses applied, in that case you can have corrosion fatigue. And if hydrogen, through any of anodic processes leading to hydrogen production in the cathodic process, the hydrogen can enter a metal and cause hydrogen embrittlement and thereby causing premature failure as well. What is common in all these forms of corrosion are that they involve electrochemical reactions, and because of that they can be measured. And the way to measure is by use of Faraday's law. Faraday's law relates metal or amount of metal which is corroding or going into the solution, or in electroplating case coming out of the solution to the charge which is passing through a cell. So charge, which is basically current times time, can be related to mass of material loss in case of corrosion. Now, second law of Faraday relates that weight lost in corrosion to the equivalent weight. So if a certain quantity of electricity is passing through the cell, in that case the mass lost will vary depending upon equivalent weight, which is basically atomic weight divided by number of electrons involved in the reaction. So the overall corrosion rate or the mass lost can be related to current, at the same time during which that current is flowing, and equivalent weight of material. F, which is Faraday's constant, is basically charge of 1 mole of electrons. Now, in terms of corrosion measurements, we want to actually measure rate of mass lost per unit surface area in a given time. So because of that, you can take that Faraday's equation and divide it by area and time, and if you do that, you can actually then rewrite that equation where corrosion rate depends upon small I, which is current density, which is current divided by area, and thereby you can determine corrosion rate by just measuring current which is passing through a given electrochemical cell in given time. So in this lesson, what I tried to introduce was that corrosion of metals is electrochemical process, which means that metals which are corroding are undergoing oxidation. To do that, you need an oxidizer or something to consume those electrons, which is also called reduction reaction. There are different forms of corrosion. It's not just general corrosion. There are localized corrosion forms, but all of them involve electrochemical processes in their mechanism. Because of that, the current which is passing through the cell, whether it's localized or uniform, can be related to either localized corrosion rate or uniform corrosion rate. And that can be measured by measuring current that can be related to instantaneous corrosion rate in labs or in the field. So in next module, you are going to learn about corrosion testing